Hello again. Today we're going to be talking about indeterminate forms and using L'Hopital's rule to solve. Okay, so there are 7 indeterminate forms. Here are the 7 different indeterminate forms. An indeterminate form, just to explain formally, is a pattern that you get when you're trying to evaluate a limit, and these 7 patterns don't have an immediate answer to them. Like a small number divided by a small number, it could wind up being small, it could wind up being large, it could wind up being 14. Could be anything. That same thing is basically going to apply to all 7 different indeterminate forms that you immediately don't know what the answer is just based on the form. Okay, now as we saw in the last video, these two, 0 over 0 and infinity over infinity, we have a way to solve those using L'Hopital's rule. But the other indeterminate forms, we've seen these two in the past, and we were able to solve them using like some algebraic simplification techniques, or maybe using trig identities or using conjugates. But we're going to be exploring problems where none of those techniques would work, but we're still going to be able to solve them using L'Hopital's rule in the very end. Also, these 3 exponential rules, they're all dealing with, exponential patterns, 1 to the infinity, 0 over 0, or, 0 to the power of 0, or infinity to the power of 0. Those we could not talk about at all before we got to L'Hopital's rule, because there's no good algebraic way to manipulate an exponential in order to get something to cancel to make it solvable. There was just no way to do that. But we will have a technique now that we know L'Hopital's rule. So let's look at some problems. Now, we've already done 0 to the 0, infinity to the infinity. So all the problems I'm going to be showing you are going to be for the other 5 indeterminate forms, and we'll show you how to simplify and eventually use L'Hopital's rule to get the final answer. Okay. So the first one is a limit of x times ln x. See, I got the wrong marker. Limit as x approaches 0 from the right. The reason we're doing it from the right is because the natural log function is undefined for negative values x, so you can't even do a limit from the left. So we have to do it from the right so that the ln function is well defined. Okay, anyway, so if we plug in 0 into the first part, we just get 0. And if you approach 0 from the right, ln of x plunges down to negative infinity as you approach 0 from the right. Therefore, this is 0 times negative infinity. Now, it really doesn't matter whether we're talking about negative infinity or positive infinity. We still say it's the pattern 0 times infinity. Doesn't matter whether it's plus or minus infinity, really. So this is one of our 7 indeterminate forms. Okay, so how are we going to use L'Hopital's rule to solve this? Well, L'Hopital's rule, you need to have a fraction, so we need to turn this into a fraction. So take one part of the product, and we're going to move it into the denominator and flip it upside down. So instead of multiplying by x, we divide by 1 over x. Okay. Now that it is a fraction, we can apply L'Hopital's rule. Note, when you're doing this, try to think about which one of these two things you'd rather flip to the denominator. I chose to flip x because you get 1 over x and the derivative is pretty easy. Whereas if I tried to flip ln of x into the denominator, it would become 1 over ln of x, and that'd be a little bit more annoying to find the derivative of 1 over ln of x. Whereas 1 over x is just x to the negative 1. That's pretty easy to take the derivative of. Anyway, so now if we try to make x approach 0, this is still going to negative infinity. The denominator is approaching positive infinity, and therefore that's now infinity over infinity. Remember, I said when it comes to infinities, it really doesn't matter whether it's plus or minus. This is still the infinity over infinity pattern. Okay, so we can use L'Hopital's rule. Derivative at the top is 1 over x. I'm going to write that as x to the negative 1 power. The derivative at the bottom would be negative x to the negative 2. Okay. We can simplify that to be the limit as x approaches 0 of negative, and then x to the negative 1 divided by x to the negative 2 You could flip the x to the negative 2 up to the top to become x to the positive 2. Then you would have x to the negative 1 times x squared. You add the powers and you get x to the 1. So just x. And then as x approaches 0, negative x just goes to 0. So your answer is 0. Okay. Let's look at another problem. Okay, this is going to be 1 over x squared minus 1 over tangent of x. And we're going to be doing a limit as x approaches 0 from the right. Now, I suspect this time it probably didn't matter whether it was right or left, or they could have just said x approaches 0. I think that would have been okay. But anyway, let's just stick with 0 from the right. Okay, 1 over 0. So whenever you have a constant over something that approaches 0, that approaches infinity. Like, see, 1 over 0.1 is 10, 1 over 0.01 is 100. And as your denominator gets smaller and smaller, your fraction gets larger and larger. Therefore, whenever you have a constant over 0, that's going to go to infinity. Okay, so that's going to infinity. And this is also going to 1 over 0, so that goes to infinity. So we have infinity minus infinity. Now, I should be a little bit careful. When I was explaining that when you have like the pattern infinity over infinity, it doesn't matter which infinity you're going to. That's true. But for this pattern, infinity minus infinity, the two infinities have to be literally positive infinity. So that you have something going to positive infinity minus another thing going to positive infinity, then that's an indeterminate case. Okay. So we want to try to apply L'Hopital's rule. So this time we're going to get a common denominator. So multiply the top and bottom of this by tangent, and multiply the top and bottom of that by x squared, so that they both have the same denominator of x squared tangent x. We can then combine that together into one fraction, giving tangent x minus x squared all over x squared times tangent x. And we're still doing a limit as x approaches 0 from the right. Okay, if you try to plug in 0, we now have 0 over 0. Great. So we can use L'Hopital's rule now. Okay, so by L'Hopital's rule, derivative top, the derivative tangent is secant squared, and then minus 2x over product rule. So derivative first would be 2x. So 2x times tangent x plus x squared, and then the derivative of the second would be secant squared x. So x squared secant squared x. Okay, let's try to plug in 0 into that. Oh, I can see that, oh no, secant of 0, secant is 1 over cosine, and cosine of 0 is 1. So secant of 0 is 1 over cosine of 0, so 1 over 1, so it's 1. So that's going to 1. That's going to 0. This is going to 0 times 0 is 0. And 0 times 1 is 0. So the top is 1 and the bottom's going to 0. And whenever your bottom's going to 0, it's going to go to infinity. You know, 1 over 0 goes to infinity. Now you should be a little bit careful because you need to pay attention to whether you're approaching 0 from the right or the left, like from positive numbers or negative numbers. Because like if you're going to 1 over 0 from the left, like negative numbers, you're going to be going to negative infinity. Whereas 1 over 0 from the right or from positive numbers, you're going to be going to positive infinity. So let's look back. As you're approaching 0 from the right, that would be a positive number. Tangent of a small positive angle would still be positive. That's positive. And that's 1, which is positive. Yeah, so this would be approaching 0, but from positive numbers. So let's put a little plus right there just to remember that we're approaching 0, but from the positive numbers. Therefore, positive over positive 0 goes to positive infinity. Okay, so that's our answer, positive infinity. Okay, so those were examples of 0 times 0 and infinity minus infinity. And both of those were just straight up turning the equation into a fraction and then applying L'Hopital's rule. Now, the next examples are going to be exponential examples, and it's going to be a little bit harder to turn an exponent into a fraction. Okay, so let's say we have a limit as x approaches infinity of x raised to the power of 1 over x. Okay, so the base of the exponent is going to infinity, and the top, 1 over a large number, is going to go to 0. So we have infinity raised to the power of 0. And that was on my list of indeterminate forms. So we don't know what's happening yet. But we want to try to change this into a fraction somehow. And so the trick is we're going to be using the logarithm to change the exponent into a fraction. Now, the way I like to do this, to keep track of what I'm doing, is I like to assign a value to this limit. I'm going to call this limit A. You can think of A as standing for answer, if you want. Anyway, I'm now going to take the natural log of both sides of this equation. Like that. Okay. Then, this is a property dealing with limits and the logarithm function, that since log is a continuous function, you can basically sort of switch the order of this. Write the limit on the outside and the ln on the inside. Okay. Then we can use natural log properties to bring this exponent down in front of the logarithm. And then it's pretty easy to change that into a fraction. Now, just checking, we have infinity over infinity, so we're ready to use L'Hopital's rule. Derivative of the top is 1 over x, the derivative of the bottom is 1. And then as x approaches infinity, 1 over infinity goes to 0. So you have 0 over 1, which is 0. But that's not the answer. Because remember, we took the natural log of everything first. Therefore, ln of a equals 0. So if ln of a equals 0, what is a? Well, now you have to raise both sides to the power of e. So the e and the ln cancel, and e to the 0 is 1. So a is 1, where a was the limit. So the answer is our limit equals 1. So when you're doing this, you take the natural log, change the exponential equation into a fraction. You should have 0 over 0 or infinity over infinity at that point. You can then use L'Hopital's rule. Then you have to remember at the very end that ln of a is that number, and so your final answer will be e to the power of this number. So this is, using the letter a and doing ln of a is just a way for me to keep track of the fact that I need to do an exponent at the very end to undo the logarithm that we did at the very start. Okay, so let's look at another example. Now really, all three exponential forms are going to be the same way of just using the logarithm to change it to a fraction and then applying L'Hopital's rule. But let's look at a couple more examples. Okay. Let's do a limit as x approaches 0 from the right of x to the x. Okay, so this is 0 to the power of 0, which is another one of our indeterminate forms. Okay, so if I let this equal to a and then take the natural log of both sides, I'm going to speed up the process by just go ahead and put the ln inside of the limit, because I know that you can shuffle that order. Okay, bring down the power of x, rewrite that as a fraction. Okay, then as x approaches 0, we get ln of 0, which plunges to negative infinity, over 1 over positive 0, which is approaching positive infinity. So we have infinity over infinity, and therefore we can use L'Hopital's rule. Okay, so by L'Hopital's rule, derivative of the top would be 1 over x, or x to the negative 1. The derivative of the bottom is negative x to the negative 2. I think we did this exact problem a couple of problems ago. But anyway, so that will simplify to be negative x, and then the limit as x approaches 0 is 0. But that means ln of a is 0, therefore a is e to the 0, which is 1. So final answer is that this limit equals 1. Okay, let's do another one. I think that's what I want. Oh, this needs to be going to infinity. Okay, so we're doing a limit as x approaches infinity of 1 plus 1 over x, all raised to the power of x. Okay, so that's going to go to 0, so 1 plus 0 is 1 to the infinity. And 1 to the infinity was one of our indeterminate forms. Okay, so let's let this whole thing equal a, do the natural log of both sides. So ln of a equals the limit as x approaches infinity of ln of that equation. Use a log property, and then turn it into a fraction. Now, as x approaches infinity, that is going to go to 0. So we have ln of 1 over 0. Well, ln of 1 goes to 0, so we have 0 over 0, which is an indeterminate form. Okay, so now we can use L'Hopital's rule. The derivative of the top, and this is going to be the chain rules. We have to do 1 over the inside. Ooh, that's going to get a little ugly. So 1 over 1 plus 1 over x times the derivative of the inside. Derivative of the inside would be 0 minus x to the negative 2. So in other words, minus x to the negative 2, you could write that as negative 1 over x squared. And the derivative of the bottom, oh, that's also negative 1 over x squared. Well, that's convenient. We can just cancel those two. All we're left with is that. As x approaches infinity, 1 over infinity goes to 0. So you just get 1 over 1, which is 1. Which means that ln of a equals 1, and therefore a is e to the power of 1, or in other words, just e. Sorry, that's a little bit off camera. So a equals e to the 1. All right, so this limit was equal to e. Okay, let's look at one last example. Which is going to be this exact same limit, but this time we're going to be doing a limit as x approaches 0 from the right. Okay, so let's see what happens. If we try to plug in 0, 1 over 0, positive 0 that is going to be going to positive infinity. And plus 1 is still going to be a very large number, positive infinity, raised to the power of 0. Okay. So, that isn't exactly what I was wanting. Anyway, let's go ahead and continue with this one. Okay, so infinity raised to 0 is one of our indeterminate forms. So set this equal to a, take the natural log of both sides. Okay, so ln of 1 plus 1 of x to the x. Now the steps here are going to be pretty much identical to last time. Bring down the power. Rewrite as a fraction. That's now infinity over infinity, which is indeterminate. Okay, so by L'Hopital's rule, the derivative of top is 1 over 1 plus 1 over x times negative x to the negative 2. The bottom's negative x to the negative 2, so that will cancel with that. Then, as we approach 0 from the right, this approaches infinity. So we have 1 over a large number, which goes to 0. Therefore, ln of a equals 0. Therefore, a is e to the power of 0, which is 1. So final answer is 1. Okay, so I think that's a good place to stop for now. Going to be coming out with some more videos very soon. See y'all later. Have a good day.